All right. Um, now, this is it. This is the last class. So, finishing off chapter 7. And really, the purpose of today is for those of you who are doing or might consider doing homework 7, then this will be helpful with that. Basically, it is absolutely necessary to do a couple of problems because the lowest homework gets dropped. So, okay.
And our homework is basically just due next Friday, next
Uh,
Thursday.
I prefer Thursday because Friday's commencement and all that.
Oh, yeah.
So next Thursday, like in 9 days.
10 days.
Yes.
Yeah. Yeah, so I want to have everything by then. Okay. We're still dealing with Laplace's equation, Poisson's equation, so elliptic problems. And we've seen separation of variables for hyperbolic and parabolic problems. So the procedure is very similar. But I want to have some concrete examples for you. Okay, so first I'll describe a general procedure for Laplace's equation in a rectangle. So Laplace unity was 0. So x between 0 and L, y between 0 and M. And then we have, so we don't have initial conditions. This is not a time-dependent problem. We have boundary conditions. Actually, I'll use a picture. We're just reading formulas, it's hard to keep track of which boundary conditions apply where. So, okay, so this is x equal L, and this is y equal to M, so the boundaries of our rectangle. And then, for this example, I'm going to let, well, at x equals 0, the solution will be 0 on this boundary. And at x equal L, we'll have a solution also be 0. So this boundary condition is going to be a function of y. It's also a function of y. It just happens to be 0 in this case. And then along this boundary at y equals 0, so u of x 0 is some specified function a of x. And then here we have u of x and y is equal to m in some given function b of x. Okay. So the thing is, you can think of it somewhat being like a wave equation, because, for instance, if you have utt equals uxx, second order wave equation, you have boundary conditions, and you also have two initial conditions. Well, here we have uxx plus uyy equals 0, and so it's expected that you'd have your boundary conditions, and you could almost think of these like initial conditions in terms of making sure the number of conditions are correct. It's just that because the sign is different, the behavior of a solution is completely different. Because wave equation is utt minus uxx equals 0. Here we have uxx plus uyy equals 0. So mathematically, a lot of it can be done the same way, but you just get a very different result. Okay. All right, so we do separation of variables, and we'll just take it from the top because the equation is quite different. So we assume that u of xy is big X of x, big Y of y, and we substitute it into the PDE. The Laplacian of u is 0. And what we get is, so Laplacian of u is uxx plus uyy, so that's going to be big X double prime y plus big X big Y double prime is 0. And then we rearrange. So we get big X double prime over big X, which is equal to minus big Y double prime over big Y. And this depends on only x, this depends on only y. So like usual separation of variables, both expressions must be equal to a constant, which we'll once again call minus lambda. So that gives us two ODEs. One, what? Someone say something? That was weird.
It might have been outside.
Oh, okay. All right.
It's probably a word.
Yeah, that's all we need. Number of birds. Okay, so we have big X double prime plus lambda big X is 0. And we've seen this problem a zillion times. We know what the solutions are. And with boundary conditions, big X of 0 and big X of L are both 0. So homogeneous boundary conditions. And then the ODE for Y, almost the same. Y double prime minus lambda Y is 0. Now the thing is, I could have put the minus on either one of these. I chose to put it here. Now, how do you make that choice? You want the plus in the ODE for whichever variable is going to have homogeneous BCs, boundary conditions. Whether it's Dirichlet or Neumann or mixed, if you have a homogeneous boundary conditions on two sides, two opposing sides like we do here, then you want that ODE to have a plus, then the other one gets the minus. So if my boundary conditions have been different, I have like a of y and b of y over here and zeros over here, then I would have gone the other way with this. And actually, I believe that is what I do in a different example. What if none of them are homogeneous? That can happen. The best thing to do in that case is what we've done for time-dependent problems. You make boundary conditions homogeneous by subtracting off like a function like w of x, y, like a linear function or quadratic function that satisfies the boundary conditions. And then you can force two of the boundary conditions to be homogeneous and then proceed like this. So, all right. Now, so what are the general solutions? Okay, for this first one, we've done this a zillion times. When it's this kind of ODE and these Dirichlet boundary conditions, what kind of functions are your solutions? Sine. So we have big X sub n of x is going to be sine n pi x over L, and n is equal to 1, 2, etc. And your eigenvalues, lambda n, are n pi over L squared. So now you can go ahead and use that in this ODE. Now, because for satisfying these boundary conditions, we must have lambda be positive. And we've been through all that before. We know how that story ends. So here's where things get different. If I now have this ODE, y double prime minus lambda y is 0, and we know that lambda is positive, what kind of functions do we get for these solutions?
Hyperbolic.
Yeah, hyperbolic sine and cosine. Now, normally you say, okay, I can have like a constant times hyperbolic cosine plus another constant times hyperbolic sine, but there's actually an easier way to write these because we now have these boundary conditions to deal with. So I'm going to write solutions in this form. So yn of y is going to be a constant times, and we'll go ahead and use a hyperbolic sine, sinh n pi y over L. So the same eigenvalue. And this is convenient because if I set y equals 0, I get 0. So this term will drop out and make way for my other term. Now you might think, oh, I'll put a hyperbolic cosine here. I could do that. but it's not convenient. Here's what is convenient. Hyperbolic sine of n pi m minus y over L. Okay. And the reason why I do that is if I plug in y equal to big M, this term goes away. It makes it easier to find these constants to satisfy these remaining two boundary conditions. So at this point, these two boundary conditions automatically satisfy. I still need to satisfy these. So I need to satisfy the BCs at y equals 0 and y equals m. I think is this shift, this is a shifted and reflected hyperbolic sine, which can be expressed as a linear combination of hyperbolic sine, hyperbolic cosine, because hyperbolic functions have similar sum and difference identities as regular trigonometric functions, sines and cosines do. So I'm just taking advantage of that here. So really, I'm basically asking, take it on faith that these give me two linearly independent solutions, which is really all I need. But it's easy to see that these are linearly independent because they're not scalar multiples of each other. No. So it may not be the linearly independent solutions you'd expect, but they do work, very convenient. All right, so now I have my xn of x, my yn of y. So if I can multiply them and have solutions of my PDE that automatically satisfy these boundary conditions. So I just need to write linear combination of them that will satisfy these boundary conditions, and then I'm done. All right, so any questions so far about what we're doing here? All right, so now
AX and BX, you're going to have to a combination of sine and cosine.
Well, actually, it's all going to be sines or hyperbolic sines.
Oh,
In order to satisfy these two boundary conditions, it's kind of like how we satisfied initial conditions before.
Okay.
Yeah, and you'll see that in a moment. Okay, so now my solution, u of xy, is going to be a sum of my xn of x times my yn of y. So first thing to do, for first boundary condition, I'm going to set y equals 0. So that's going to cause this term to drop out. So now I'm going to have bn sinh n pi m over L times sine n pi x over L. Okay, and this is supposed to equal a function on the lower boundary, a of x. Separately, if I plug in y equal m, and you get something similar. So this term will go away, and I'm going to have an sinh n pi m over L sine n pi x over L equal b of x. Okay. Now, I'm going to group these together because these are constants. Sinh n pi m over L, there's no x or y there, it's a constant too. So you can think of what I have in parentheses here as the coefficients of a of x and b of x in this Fourier sine series. So now I can find those coefficients just like before. So And you'll recognize the formulas from previous homeworks. So for the first one, Bn, and in retrospect, considering I have Ba and A and B, I probably should have switched these letters, but too late now. So I could say this is equal to inner product of sine n pi x over L with A of x over inner product of sine n pi x over L with itself. So that's going to be, well, this denominator here is going to be L over 2. So I'm going to get 2 over L integral from 0 to L of A of x sine n pi x over L. And this is for n equals 1, 2, etc. So now all I have to do is rearrange this, and I've isolated Bn. So Bn is going to be, I just had to divide by this constant here. So I'm going to get 2 over L sinh n pi m over L times this integral. Okay. And that's it. That's my, so that's my coefficients to satisfy the bottom boundary condition. And I could do the exact same thing for the top boundary condition. It's going to be exactly the same formula, basically. So it's going to be An is 2 over L sinh n pi m over L, integral from 0 to L, B of x sine n pi x over L. And that's it. That's your solution. Okay. Is there any questions about this? All right. Now I mentioned like what happens if none of the boundary conditions are homogeneous. So there's a way to deal with that using methods of section 6.6. What if a PDE is non-homogeneous? So you have Poisson's equation. Laplacian of u is equal to f. So once you have these eigenfunctions for one of your variables, like x in this case, you can expand your right-hand side, big F of xy, in the base of eigenfunctions, just like you did for non-homogeneous time-dependent PDEs. So basically you would get a non-homogeneous ODE, and that's what you would have in this case. Okay. So essentially what's happening is for xn of x, you are solving an initial value problem. Well, actually, no, that's not true. Okay, what you're accustomed to from previous chapters is you would solve a 2-point boundary value problem because you'd have your regular boundary conditions, Dirichlet, Neumann, etc., or you might have periodic. Now, what you would do before, in the time-dependent case, for Tn of t, you would solve an initial value problem, which may or may not be homogeneous. It would have initial conditions. Now, you're solving for yn of y. That is also a 2-point boundary value problem. Okay. Because instead of having initial conditions, you have conditions specified at both boundaries. And this 2-point boundary value problem, the PDE, the ODE, is not necessarily homogeneous. So whether it's homogeneous or not depends on whether it's Laplace's equation or Poisson's equation. So if it's Poisson's equation, the Laplace of u is equal to big F, that's going to make for a non-homogeneous boundary value problem. And then there's a question of, is it a classical solution? In order for that to be the case, you need compatible boundary conditions. So for instance, suppose the solution is equal to 0 on two of the boundaries. On the other two boundaries, if the boundary data is not 0 at the endpoints, you have a discontinuity. So chances are your solution will not be a classical solution because you're going to end up having Gibbs phenomenon at these corners. So that's something to be mindful of. Okay. All right. Now, so I'm going through this procedure now because there are two problems in the Chapter 7 homework that have you do this, solving a elliptic problem on a rectangle and with different boundary conditions. And what happens is, and I got to confirm this by examining the problems again. Okay. Just to make sure. Okay, chapter 7. Okay, so for instance, in one of the problems I gave was problem 4, and that is set up like this one. That's the example I did, where you'd have homogeneous boundary conditions on the left and right side, and then I gave one other problem 8 that has it's the opposite situation. So at the bottom and top boundaries, you have homogeneous Dirichlet boundary conditions. So in other words, your minus goes with the x equation rather than the y equation. So the roles of the variables are reversed in problem 8 compared to problem 4. Otherwise, the solution procedure is no different. And then problem 8 has a bonus, if you will. As a part B, it says, is there a point in your domain where the solution can be equal to 0? And so there are a couple problems in this chapter 7 set that deal with a maximum principle and similar results that I've been talking about. So that's what you keep in mind to answer questions like that. Okay. All right. So that's actually all I have for. So what I've done here is a blueprint for handling problems 4 and 8, and the other problems I gave in this 4 and 8. The other problems I gave number 1 and number 5. One's prove a Green's identity, the one I didn't do in class, and number 5 also a maximum principle question. So anyone doing homework 7, there's your plan. Okay. During the remainder of the time, make sure I'm still recording here. Okay. I have a different sort of elliptic problem to discuss. So solving Laplace's equation on a circle, so you're solving it within a disk, and so your boundary, of course, is a circle, and you have boundary data specified in a circle, and how do you take that into account? So it's a similar procedure. You still use separation of variables, but because it's a disk, you want to work in polar coordinates. And I've shown you the Laplacian in polar coordinates. It's a bit uglier. So you have different ODEs to solve. Okay, so we have, I'll focus on Dirichlet boundary conditions. So the Dirichlet problem on this. So Laplacian u is equal to 0. Okay. It's less than. So disk of radius r tilde. The reason I have r tilde instead of r is I need R for something else when I do separation of variables. Okay, so working on disk centered at the origin. Yes, it's supposed to be a disk, believe it or not. Radius R tilde. Okay, and we have different boundary conditions. We'll set U equal to G on the circle centered at the origin, radius R tilde. Okay. So we have Laplacian and polar coordinates. So I write it out that way. U R R plus 1 over R U R plus 1 over R squared U theta theta is 0. And so then G is, so we can work in polar coordinates, so G is now considered a function of theta, so that'll be more convenient to work with. Okay. So now we do separation of variables all over again. So I let U be equal to big R of R, big theta of little theta. You have to write these the way that distinguishes them. But so we go ahead and substitute into PE again, and we get big R double prime, big theta, plus 1 over little r, big R prime, big theta, plus 1 over R squared, R theta double prime is 0. And then we go ahead and rearrange this, isolate everything with, depending on R on one side, everything depending on theta on the other side. And we get minus little r squared big R double prime plus R big R prime over big R, which basically comes by multiplying through this entire equation by little r squared. And that has to equal big theta double prime over big theta. And we'll set these equal to a separation constant, again, minus lambda, because we're going to get the same old ODE for theta. Okay. Now, since theta corresponds to our angular value in polar coordinates, this boundary condition really is boundary condition in the R variable, because we have a fixed value of little r equal to big R tilde, or that's specified. But what boundary condition should this satisfy for the theta variable? Because that determines how the solution varies as I go around the origin. So little theta is a variable, independent variable that ranges between 0 and 2 pi. So you can think of it as being a function. So this is ODE. Defined on this interval. So I need boundary conditions for this interval. What would be appropriate boundary conditions? That would work, but it's not general enough, because how do we know for sure that the solution really, because that would make the solution equal to 0 along this this whole line here. So that boundary condition won't work. What would be a different one?
Both of them having to be equal to each other?
Which is what kind of boundary condition? What do we call that? Periodic. Yes. So we need a periodic solution. So theta of 0 equals theta of 2 pi. And the way we normally specify these boundary conditions is we require the same thing derivatives, although that's going to follow automatically. And what that means is we're going to get sines and cosines. So big theta of n of little theta is going to be constant. cosine of n theta plus b sub n sine of n theta. So that's our general solution. That's 2 pi periodic. Okay. So that's that ODE. But now we have this other ODE to solve for big R. So we have R squared, R double prime, plus big R prime, minus lambda R. But that's going to be, but lambda n is going to be equal to n squared. So we're going to have minus n squared R. So we fill that in up here. It's equal to 0. So now that is the ODE that we need to solve. And this is a special type of ODE. It's called an Euler equation. I know many things are named after Euler.
Everything is.
Yeah, Euler, Gauss, yeah. Not much left. Okay. Now, this is an ODE that is sometimes covered in ODE classes, but not ours. I don't think it ever comes up in Math 285, unfortunately. Which is kind of a shame, because it's not really that hard to solve. You let, let's change variables. Z equal to ln of little r, your independent variable. And if you do that, then this becomes a second order ODE in constant coefficients that can now be solved using methods that are taught in Math 285. So let's cut to the chase here, because I don't trust myself to carry out the manipulations correctly in my adult state of mind. Here's the general solution. After undoing this substitution, you get big R of little r is a constant. I'll index these by n. Okay. So we have a sub n r to the n plus b sub n r to the minus n. And n is equal to 0, 1, 2, etc. So we just have to choose these coefficients in order to satisfy the given boundary condition on the circle of radius big R tilde. Okay. So now I can write down the entire solution in order to figure out these constants. It's going to be similar to what I just did on this board, but I got to erase it all anyway because now we're working in polar coordinates. Okay. So now we have our solution u of r theta is okay. Now, so first of all, for one thing, I'm going to let b0 equals 0, and the reason for that is because r to the minus n, okay. Well, actually, in that case, it's 0. Well, the thing is, if I set n equals 0, I have my solutions equal to a naught plus b naught. I have two constants where I really only need one. So in order to avoid having two terms for the same solution, I'll just set that equal to 0. So now we're going to have a0 over 2 plus the sum, n equals 1 to infinity, of okay. Oh, all right. say b0 equals 0 for convenience. I'm also going to set b sub n equals 0 for n equals 1, 2, etc. Because if we have r to the minus n, where n is a positive integer, these are undefined at the origin, because we're dividing by 0. So my general solution, let's see. Oh. Okay, I have a notation problem, and I need to fix that. I guess the same thing went unchallenged in my notes. Okay. I'm going to go back and change notation just to avoid problems later. Okay. I have an and bn for my theta solutions. I also have an and bn for my r solutions. They're not the same. I've already been just talking about these, so I'm going to leave these the same. I'm going to change these. I'll call these alpha n and beta n. Okay. So I still, what?
Sorry, why is R to the negative n not defined?
Well, because 1 over r to the n. And if r is 0,
If R is 0.
Yeah.
Oh, then R is 0. Oh,
yeah,
okay.
yeah. Like in this case, if I have n equals 0, it's not really a problem. I just have a0 plus b0. I have two constants when I only need one.
Right.
So b0 and bn are set to 0 for different reasons. Yeah. Okay. So to avoid confusion, or more confusion, I'll just call these constants something else that I haven't used yet, but I'm about to use them to satisfy the boundary conditions. Okay, so be sure to change that in your notes. It's alpha n and beta n. Okay, so now I can go ahead and all right. So really, I'll take this from the top here. N equals 0 to infinity of Rn of r, theta n of theta. Okay. Now, let's summarize what everything is. So it's all in one place and actually correct. Theta n of theta is alpha n cosine n theta plus beta n sine n theta and starting from 1. Theta 0 of theta is that's just alpha 0. Okay, because when n equals 0, we're not going to have a sine term, and cosine of 0 is 1. Okay, so those are our solutions for that case. Big R and of R is just going to be, I need R to the n in here. And only for, well, this is for n equals 0, 1, 2, etc. And I can multiply that by any constant if I want. Now, I could just leave it alone. And then I only have the constants, these alphas and betas. But it turns out to be convenient to include a constant factor in this. I'm going to divide by big R tilde and raise all of that to the nth power. Okay, so because this is a solution to homogeneous ODE. If I multiply it by a constant, it's still a solution. So this constant is the most convenient choice. So now I have tossed out everything I don't need, tossed out things that I don't want, because I definitely don't want these terms in there. Because the only thing left is the R to the positive n. So now I still have that. Okay, now I can assemble my solution. Okay. So I'm going to write the n equals 0 term separately, because when n is 0, this is just 1. All I have is alpha 0. But I'm going to scale that by 2. Actually, I'll just go ahead and put that here also. Okay. the factor of 2 is not necessary, it's a convenience, and it does come up in other problems, but I'll explain the convenience when I get to that point. All right, and then n equals 1 to infinity, and now I have all these solutions. So I have little r over big R tilde to the nth power times alpha n cosine plus beta n sine. Okay, so now I have my solution. I just need to find my alphas and betas, and then I'm done. Okay. Now, I'm going to substitute little r equal to big R tilde. So this will stay the same. What's going to happen in here?
That goes to 1.
Yeah. So
Just
these will cancel. So then that's why I made that choice. So then all that goes away, and I have a more convenient expression. That's alpha n cosine n theta plus beta n sine n theta. And this has to be equal to g of theta. That's my boundary condition. So now I just have an ordinary Fourier series for g of theta. So, and we know what those coefficients are. So alpha n is going to be, 2 over L, so that's 2 over 2 pi, so that's 1 over pi, and it go from 0 to 2 pi of g of theta cosine n theta. And this is why I need the factor of 2 over here. So I can define these all the same way. Because the integral of cosine n theta squared is, from 0 to L, is L over 2 when n is non-zero. It's equal to L if n equals 0. So because of that difference, that's why I put that over 2 here, so I can just use this definition for all n, 0, 1, 2, and so forth. And then I have my beta n, that's 1 over pi g of theta sine n theta. And this is for n equals 1, 2, and so on. Okay, so that's it. That's the solution of my Dirichlet problem. Now, if this had been a, let's see, now if this had been a Neumann problem, so in that case, I would be looking at the derivative of u with respect to r, because on a disk, the normal is pointing this way. That's the r direction. So I'd be looking at du dr is equal to something, and then I'd have to differentiate this with respect to r using the power rule. So that's something, so it can be worked out. You get some extra factors of involving r tilde in there, but it can be done. Okay, so any questions about this problem solved on a disk? So separation of variables once again. But now you just had a different ODE to solve in the r direction just because the Laplacian and polar coordinates are so different. But once you have that solution, the rest of the procedure is essentially the same as you've seen in many other cases. Okay. Okay. All right. Now, how much time do I have? Oh, sorry, there's no analysis, is there?
No.
Don't worry, I'm not going to just keep going. I have one thing to cover, and that's it.
Maybe kill stories.
No.
Story time.
I think it's making a class by itself. It will be interesting.
Story time with Dr. Bain.
Or double enders.
Oh, we all have them.
That's our KSS meeting? Okay, I didn't mean that in a way, I'm sorry.
Yeah. Okay. All right. Now, there is one other way to solve addition problems. Actually, a formula for a solution. This is section 7.8, Poisson's formula, or Poisson integral formula. Okay. So what I can do is, so my existing formula for u of r theta, I have 1 over pi, and if I take my previous solution, all my constants, my alphas and betas, they're defined in terms of integrals. So if I put those formulas in, I put those integrals into the solution formula, and then I move everything inside the integral, all the constants, etc., except for this 1 over pi, this is what I have. It's an integral from 0 to 2 pi, and then what's left? I have 1/2, and then I have the sum of r over r tilde to the n, and then I have cosine n theta plus, cosine n theta, cosine n. Now here I need to use a different letter. This always comes up in homework sometimes when people take the formulas for coefficients and put them into the solution formula. So you have these integrals inside. When the integral is written separately, it doesn't really matter what letter you use, but here it does matter because I'm integrating with respect to theta. Okay, so I need to use a different letter for one of these. I'll call it ns. Sine theta, sine ns, g of s ds. Okay, so this solution formula is exactly the same as the solution formula on the previous board. All I've done is, in the integrals, I changed theta to s just to avoid ambiguity, and I dumped the integrals into the solution formula that you have there in the middle of that board, and then I move everything inside the integral except the 1 over pi. So take a moment to convince yourself of that. Okay. All right. Now we're going to mess with this a lot to get a convenient solution formula. Okay. Sorry, it's going to drive me crazy. Oh. All right. Now, one really nice thing you can use here is, to simplify this, is a trig identity. What trig identity could I use there?
Cosine.
Sum and sum for sine. No, sum for cosine.
Difference for cosine. Yeah, so this is something that's really good to know. One of my colleagues in the department, Dr. Lee, will say there are only 3 trig identities you really need to know. There's one that, pretty much the only one that most students remember, sine squared plus cosine squared equals 1. And also this one.
Cosine plus sine is
But the sum or difference formula for cosine and the one for sine. That's very different. If you have those, if you know those 3, you can pretty much derive all the rest of them.
so this is cosine n theta minus ns.
Yes. So let's go ahead and condense that. So already this will make it a much simpler expression. All right, so I still have this, and I have cosine n theta minus s. I'll factor out the n. G of s ds. Okay. Now the next thing I'm going to do is, let's get complex. We're going to write the cosine in terms of complex exponentials. So that would be e to the I n theta minus s plus e to the minus I theta, I to the I n theta minus s g of s ds. Now, cosine of theta is e to the I theta plus e to the minus I theta over 2. So I do need a factor of 2. I'll just put it out here. Okay. Next, what I'll do is I'm going to lump in these complex exponentials with the r over r tilde, because notice this is something raised to the nth power, and this is something that's raised to the nth power. So I can take advantage of that. Okay. Actually, by putting a 2 out here, I don't need it here. So that becomes a 1 now. So, forgot about that. Okay, so I have 1 plus, I'm going to have I'll write this as 2 separate sums. So I'm going to have r over r tilde e to the I theta minus s, all raised to the nth power, plus a separate sum, r over r tilde e to the minus I theta minus s, all raised to the nth power. Okay. Now, when you have a constant, I mean, this is an expression independent of n, that's being raised to the nth power. I have one here, I have one here. And I have a series like that. So I'm taking 1 plus c squared plus c cubed and so forth. What kind of series is that called?
I mean, it has a limit of.
It's a geometric series. And this will converge as long as this is less than 1 in absolute value. But we're solving on a disk of radius big R tilde. This is an absolute value 1. Little r is strictly less because we're dealing with the interior, not the boundary. So because of that, both of these are convergent geometric series. And we have a formula for that. So the sum of a r to the n, if absolute value of r is less than 1, what's the sum? Anyone remember that?
Over r minus 1 minus r over a. No, a minus r over
You keep dancing on
A
that.
over 1 minus I.
Oh, wait.
What?
A over 1 minus I.
Yes.
Yeah. I had no idea.
Talk about splattergun approach.
No,
Yeah, okay. All right. Now, so now I'm just going to plug that in. And this is nice because then there are no more summations, because summations are a pain. The thing is, of course, the goal is to use this final formula I'm eventually coming up with to solve Dirichlet problem on a disk. But the manipulations used to get it can be useful in so many situations, and that's why I'm going through them. So it's good things to have in your bag of tricks. Okay, so I have 1 over 2 pi integral 1 plus. Okay, so now I'm going to have the first term, which is that's e to the I theta minus. Oh, okay, because it was a sum from n equals 1 to infinity, whereas this formula I wrote for the sum is sum n equals 0 to infinity. Bottom line is a is the first term, so that's what I put up top, and then I have 1 minus this. So that's r over r tilde e to the I theta minus, that should be s. Sorry, I have alpha in my notes. So I have to make sure to keep the notation consistent. And then I have a similar expression over here with a minus. Then 1 minus r over r tilde e to the minus I theta minus s, g of s, ds. Okay, so now I'd like to simplify this. The easiest way to simplify this, of course, I have these fractions. I'm going to multiply top and bottom by r tilde. I'm just going to do that right here because nothing else is going to change. So now I'm just going to have r, little r, up here. And then I'm going to have big R tilde, little r here, big R tilde here, and then little r there. Okay, so that'll be working we need to work with. Okay. Now, I have these nasty fractions. What do you do with fractions when they're added?
Or
Common denominator, which means multiplying these two. And when you do that, keep in mind these are complex. So my denominator is going to be this squared, and then I have minus 2r tilde times these two multiplied together, but their exponents are going to, okay, actually, oh, wait a minute. Because they're conjugates, okay. Oh, yeah, I'm sorry, yeah, they are going to, well, actually, that is entirely what I want. Okay, so I'm actually going to have minus little r, big R tilde times this exponential, and then later minus little r, big R tilde this exponential. Yeah, those add. But, so now what I'm going to have is e to the I theta minus s plus e to the minus I theta minus s. And then I have plus r squared. Okay. Now, here I have a complex number plus its conjugate. That's twice the real part. So the real part of this is cosine of theta minus s. So I put a 2 here, and then this becomes cosine of theta minus s. Okay. Actually, to make this completely consistent, it's really twice that. I'll put the 2 in there when I get to the next step. Okay. Now, up top, we have a big mess. So I have this numerator times this denominator plus this numerator times this denominator. Okay. All right. So it seems like just when things couldn't get worse. So one thing to keep in mind is, let's see. How's our? Yes. Okay. So now we're going to expand out all of these in the numerator. So for instance, I have little r, big R tilde times this exponential plus little r, big R tilde plus times this exponential. Added together, it's going to be the exact same thing that happens down here. So what I'm going to get is, up top, 2r, little r, big R, cosine theta minus s. That's from these terms and these terms. And then from the other terms, I have exponentials of opposing signs. They're going to cancel. I'm going to get minus r, little r squared here, and minus little r squared here. So unfortunately, nothing cancels, but things do simplify. So at least I have that. And then down below, this is what I had before. Wait, what time is it? Oh, okay. That class is getting out early. Lucky them, huh? Okay. But I'm almost done. Okay. So finally, in order to combine this, I need to put this over a common denominator, which is actually going to be pretty convenient because it's going to cause cancellation with this term right here. And it's going to cause simplification due to this term adding with this one. So things actually get simpler. So now my big fraction is big R squared minus little r squared up top. That's all I have. Same denominator. All of that times g of SDS. And that's it. So this is the Poisson integral formula for the Dirichlet problem with Laplace's equation on a disk of radius big R tilde. Okay. So to evaluate solution at any point, little r and theta, you would just evaluate this integral. Analytically, probably a pain to do, almost also something that could be evaluated numerically. Okay. Now, one interesting thing to point out is the denominator here, or this denominator here, is straight from something you learn in pre-calculus or trigonometry. It's law of cosines.
Mm-hmm.
So if you have a triangle,
A squared plus b squared minus 2bc cos of the difference, right?
yeah, so we have one side is
Right.
big R tilde, and the other side is, well, it's going to be less. It's going to be r squared, little r. And this angle is absolute value of theta minus s. Then your denominator is going to be the length of that, so the denominator is the third side squared of that triangle. Okay. Now another thing you can see if you would plug in little r equal to 0, so that would wipe out these two terms. Everything would cancel. So at the origin, u of 0, 0, would just be 1 over 2 pi integral of g of s ds, which is, what does this represent, this integral? When you divide by 2 pi.
Average.
It's the average value of u on the boundary, which is a mean value principle. That when you have a harmonic function, its value at a point is equal to the average of its values on a disk surrounding, a circle surrounding that point, which in this case includes the boundary. So this is the mean value principle that this is consistent with. Okay. Now, if you are solving a Dirichlet problem on a different domain, so not a disk, what you could do is try, this is from complex analysis, conformal mapping. Conformally map your domain to a circle, apply Poisson's integral formula on that, and then conformally map it back. So this is more general than it suggests, at least. So it can be combined with other transformations to broaden its applicability. Okay. Yes, I have covered everything. So no class Wednesday. We're all done. So get your homework in the next 10 days, and that'll be it.